All right, now this looks like a real whopper of a problem. This example I'm calling the household wiring circuit because a lot of people are familiar with the wiring in their house. They may not know that it's a parallel circuit, but now I'm telling you that it is. The way the wire runs in the house is that it comes into the circuit breaker box, and then the black wire goes out to all the receptacles, and then the white wire goes out to all the receptacles. And then when you plug in your appliance or device, you are plugging in across that black and that white wire. So you could think of each of these resistors as a household appliance. And the nice thing about that is if you blow the toaster up, is that everything else still stays on. This is like the kind of Christmas tree lights that you want. You want it so that if one bulb goes out, the rest of them stay on. In this problem, we are asked to find out what the current through each branch of the parallel circuit is. Wow, that seems like a lot of unknowns. It seems like our unknowns there seems like there's more unknown about this problem than we really do. But if we remember that the voltage is the same across every branch in the circuit, then I think that helps us. So finding out what the current is through the A branch of the circuit, well, let's just take our approach, our guessing approach, because remember, Mr. A wants you to be good guessers. So going back to I erased my Ohm's law gimmick over here. Maybe I need to put that back up because I always forget which is which. But I remember that current flow is proportional to the voltage and inversely proportional to the resistance. So here's my triangle right here. And if I wanted to find out what the current is, then I cover up the I, and then it's V over R. So I need to know what the voltage is across the circuit, and I do, and I need to know what the resistance in that particular branch is, and I do. So the voltage is simply 90 volts divided by the resistance in this circuit, which is 60. Do I really need a calculator for that? Let's see, 9 divided by 6 is 1.5 amps going through circuit A. In branch A. In branch B, again, it's the same voltage, but this time we're looking at the resistance in B, in branch B. So the same voltage divided by that resistance is equal to 9 divided by 3 amps, right? Let me check my book. Oh, good, yeah. All right, in branch C, it's going to be the voltage, 90 volts divided by the resistance in branch B, in branch C, which is 20 ohms. So that's 9 divided by 2 is equal to 4.5 amps, right? Check my book. Yep. Okay. So now we found the current through all of these branches. The next thing it wants us to find is I total. All right, well, I is equal to the total voltage divided by, in this case, the total resistance. All right, we know the total voltage, but we're going to have to find, looks like we're going to have to find this R total first. In a parallel circuit, I'm going to have to find some workspace down here. You remember that in a parallel circuit, the total resistance is found using this relationship. In this particular problem, that's going to be 1 over 60 plus 1 over 30 plus 1 over 20. Okay, stop the calculator. I want to make sure that you can do these types of problems. Remember that once you add these ups, you're going to need to invert your answer. Okay, so let's see what kind of a number you get. What answer did you get? 10 ohms is the total resistance in the circuit. You might go, what? Mr. A, you've got a 60 ohm resistor and a 30 ohm resistor and a 20 ohm resistor, but yet you're telling me that the total resistance in this circuit is less than any of the resistors in the circuit? Yes, and that's an important point, that if you're looking at a parallel circuit, the total resistance is always going to be less than the least resistor. You might have to think about that for a little bit and wonder why. Because, well, if it was 20 ohms and all the current had to go through here, it would see 20 ohms resistance. But it's not. It's got these other two paths to go down. So it is not going to see the resistance of 20 ohms. It's going to see the resistance of less because there's so many more paths to follow. Now, most of the current is going to go through that path of least resistance, but there is also these other branches where current can flow. So it's going to look like to the battery that the resistance is actually less than the least resistor of 20 ohms. If you did not get 10, you need to go back and make sure that you're doing these problems right. Remember, you may have gotten an answer like 0.1. That probably means that you didn't invert the sum of the inverted resistances. This is just something you're going to have to practice, okay? Oh, but we're not done yet. We've got our total. We wanted to know what I total is. Well, let's see. If we're trying to find the total current in the circuit, then I total is going to be whatever the voltage is. Thank goodness they told us that. Divided by R total, which in this case is 10. And it looks like the total current in the circuit is going to be 9 amps. Okay. One final check before I put this problem to bed. This is one way to calculate the total current, by finding the total resistance and dividing the voltage by the total resistance. We already found the individual currents going through each individual branch. I certainly hope that the individual currents going through the individual branches add up to the total current that I calculated. Let's check and make sure. 1.5 plus 3 plus 4.5. Yep. This is going to be 9 amps. That's going to be 9 amps. Whoa. Thank goodness. So I mentioned earlier in the video that this was a household wiring circuit, and your appliances, if you would, you go and you plug them in here. So I've tried to draw this like looking like the little face guy on the receptacles where you plug things in. One wire goes into one side of it, one wire goes into the other side of it, and this is where that's supposed to be a curling iron, I'm sorry. That's where you plug your curling iron into, or whatever else. We're talking about hair today, right? So here's your curling iron, you plug it in. Now here's the thing, if you plug in too much stuff into this circuit right here, maybe you just didn't plug in one thing, maybe you had a power strip and you're plugging everything in, like your hair dryer and your curling iron and your, I don't know, your color mixer or whatever. Here's what's going to happen. Here's what's going to happen. As soon as I find my marker, I'm going to tell you what's going to happen. And you guys did this when you were doing the circuit construction kit, some of you changed the values and the settings on your circuit and you got a lot of current to flow. What happened? When you had a lot of current flow, it caught on fire, right? And that really, really does happen. If you get too much current flow, but we don't want your house to burn down. So we have these things called circuit breakers and fuses. And what we do is I'm going to draw my symbol for a circuit breaker or a fuse is like this. It's just a little squiggly wire right here. And that's like a filament and a light bulb, but it's just a really thin piece of wire. If it gets hot, what it's going to do, it's going to break. It's going to open up. It's going to split. Now they do that with a circuit breaker so that you don't have to replace the whole circuit breaker. It's just a switch. It's a bimetallic material, but you can read about it in your book. But in any case, there's a circuit protection mechanism right here so that if you get too much current flow, this opens up, stops current flow. But does that keep your other appliances from working? No.
What's the thing in like circle, the third object?
Oh, this is a ground, right? So this is ground, and this kind of goes back where we were talking about static electricity always wants to find a ground. This is a path to ground so that you're not the path to ground. This is the path to ground. So if something happens, it has a place to go.